One of the projects that I work on is the Astra project, and this is where we're looking at, we're looking at the atmosphere and trying to answer questions like, well, if you had the ability to take some sensors, be them for wind speed or temperature, and you could put them anywhere, what would you sense with them and how would you do it? And the Astra project is very much looking at this capability. How would you get your sensor there? So let me give you some examples. So I'm sure you can understand that you can have a simulation or a model which will tell you, for example, something about the weather. So you can predict the weather based on a simulation. The problem is at some point either you have to validate your model with some real results. So for example, you actually have to go outside and test the temperature. And the big problem here is that it's quite well understood for certain distances, for certain altitudes above the planet. So in Southampton we have a weather station. This is the weather station that we have on the top of our building. It tells us a lot of information about the current weather status. And it's very interesting. Effectively it's just a bunch of sensors. That only gives us one data point, and of course it's very close to the ground. In actual fact it's probably about 4 stories high. If you want to go a little bit higher than this, obviously you can understand that the cost begins to increase. So if we start looking at, well, how else would you take your sensors higher into the atmosphere? A couple of examples here. The lower one is the Helios, which holds the record for the highest altitude aircraft. It's around nearly 40 kilometers. But these are very bespoke aircraft. They're very, very expensive to make, and obviously cost is a big issue, but obviously you can't mass produce these. On the other end of the scale, you can understand that if you wanted to take your sensor through a part of the atmosphere that's really, really distant, really, really far off, you could use a satellite for that. So the picture I have here is Sputnik, one of the first, and it traveled at an altitude of about 219 kilometers above the Earth. Now, it's important to realize that as part of the Astra project, we're not looking at space. And there is actually no formal definition of where space begins, but it's generally accepted that at around 100 kilometers above the Earth, you're kind of reaching space. So if we zoom in a little bit on this, you have the troposphere, which takes you to roughly 10 kilometers, and then you start entering into the stratosphere. And you can understand for an aircraft, okay, so some specialist aircraft may do 20, 30, 40 kilometers in altitude, but realistically you're going to get 10 to 20 kilometers out of an aircraft that you can just go and rent. So you can understand, okay, well maybe we could use an aircraft, but what about the distances up to say 60 kilometers above the planet? It's too expensive to make an aircraft to go there. You could use a rocket, of course. Rockets are very expensive as well. The reason I picked 60 kilometers here, by the way, is there's not a limitation. It would be really nice to do some science above the 60 kilometers, but we have no idea how to answer that question yet. So the area that we're focusing in is, hey, how would you take your box of sensors, how would you look at the atmosphere below 60 kilometers? And there's a piece of technology that's been used for over 100 years, and that is the balloon. And you can use a balloon to basically take your sensors very, very high into the lower stratosphere. The advantages of this are that basically the balloon is very lightweight, it's very cheap. You basically tie your sensors to the bottom of it, you let go of it. As it rises, it begins to expand, and eventually at some point the balloon gets so big that it bursts and your sensors fall back down to Earth. This is currently how weather forecasting, for example, is done. There's a thing called a radiosonde. It's about 300 grams. It's attached to a balloon of roughly 300 grams as well. And they release 2 to 3 of them per day from many locations throughout the UK. And the information that's fed back from these radiosondes is used to calculate or predict the weather in the future, which is very interesting. One of the problems with this is, though, that even though they are very cheap, if you start mass releasing pieces of electronic equipment, not only are you littering, so there's obviously some consequences there as well, but the costs begin to rack up. And so as part of the Astra project, what we're looking at is saying, okay, we want to take this balloon concept, but we want to take it to the next level. And we want to be able to say, okay, fine, we want to retrieve your instruments. Two reasons. One, for the environmental reasons, obviously, we don't want to be littering. But also, if we could say to you, hey, look, whatever science you happen to be interested in, we can take your sensor through this little volume of space here, anything up to, many tens of kilometers high. You might be interested in it, but if I could say to you, well, within 95% certainty, we could actually retrieve your sensor, then you would be more interested in saying, well, actually, okay, I can fly a more accurate sensor, for example, where accuracy effectively equates to cost. So you might be willing to put a more expensive sensor on it. So one of the key missions for the Astra project is to make this retrievable. Now, there are some complications here because the rules, so whenever we release a balloon, we have to get authorization from the Civil Aviation Authority, and if you have anything on it that acts as a control surface, so if it was a little glider, or if it had a little rudder or something on it, or even if it had a mechanism that cut the line between the balloon, you're changing its classification from a radiosonde to an aircraft, and that has big consequences. So we stick very much into the radiosonde category. We have no control surfaces. So how do we guarantee that we're going to get your sensors back with some certainty? And the way that we do this is we have a prediction model. So as we're ready, I don't know if some of you actually saw, the rest of the team are actually standing out on the airstrip there with a big balloon that they were panicking and blowing around in the wind with. So the idea is that if you've got a good enough prediction model and you know something about the wind speed, for example, you could run a model and say, well, I assume if I put this much helium into my balloon, it's going to land within this sort of area. And if you don't like that, one of the things of living on an island is that, there's a lot of water around the outside, and you certainly don't want everything to land in there. So you can vary the amount of helium that you put into your balloon. And that's pretty much the only control that we have over it. So bear that in mind. Now, we were going to cut to a video here. Now, the guys are getting blown around outside. We did try to release, so we were going to release 3 balloons today. One in the morning, which we were going to release to basically give us an idea of what the wind conditions are like. I think it's quite interesting to know that we nearly got blown over trying to release the balloon. But hopefully the guys are going to try and release it now. We're competing with an Apache, which is a landing at 11 o'clock. So we'll see how that works out. But I want to talk to you about the payload that the sort of things that we're interested in, what we actually have in here. So the picture that you see on the screen here is the actual payload. So if you saw the introduction to this presentation, you saw that there was a balloon and a very small payload. That was our first generation of payload. This is our second generation of payload, and we think this is probably a world first. And the thing that's very interesting about this is the way that we've designed and built it. So everything today has to be rapidly prototyped. It has to be rapid this, rapid that. It's a very fashionable thing. However, there is actually some engineering reasons why you'd want to do this. So if you look at the payload here, so this is just the payload. This is what you would hang underneath the balloon. You'd have a parachute in between. The ellipses around the outside are a little bit of cushioning. We put that on there just in case, although it comes down on a parachute, we just want to make sure that it's we can take some of the impact out of this. So the ellipses around the outside are very lightweight foam, the sort of stuff that your Christmas presents come wrapped in. And to cut this, we use a hot wire. So we have a hot wire that we have attached to our CAD, and basically it just etches it out for us. So very quickly, within a few minutes, we can make these rings that go around the outside, and they just clip in. There's no screws, they just clip in. The thing that they clip into is the red housing, and this housing is also rapid prototyped, so we printed this one. The reason for that is that we can do it quickly. It's a little bit heavier, so we take an impact there compared to some of the other materials that we could use. But within a CAD program, we can draw the casing that we want and have all the little mounts and everything for all the sensors that we have inside it. And we click print. The interesting thing about this is that the first one that we printed, it actually comes in 2 halves and they clip together. There's no screws, they just sort of friction fit together. We made a little bit of a mistake, and they theoretically fit together, but in practice they don't. The good thing about this is that we fixed the problem and clicked print. Admittedly, we had to wait another 30 hours for the thing to print. These things aren't as rapid as they might have you believe. But basically, within another couple of days, we could have the next housing. So the interesting thing about that is that you've got a rapid prototyped casing. And the reason that we think this is probably one of the world's first is that not only is the casing rapid prototype, but so is the electronics inside it. In order to get the electronics inside it, which is effectively a logger, so we've got a barometer for altitude, we've got a couple of temperature sensors, and we've got a humidity sensor, and we've also got a GPS, so we know where it is. And the picture in the middle is the actual model, is the actual internals that we're flying. And the tool that we're using for this is a project that actually came out of Microsoft called .NET Gadgeteer, which is a project that I'm involved in as well. And the idea here is that you don't need to know the low-level electronics if you want to create yourself something. So if you wanted to create yourself a digital camera, it takes 4 lines of code to do that. And to actually write the software, and to plug it together, basically you have little modules which are on the outside, and you can see they connect to the main board in the middle. Now, you take a hit here, so in our case, we have to carry a little bit of extra mass. This is a little bit heavier than we'd normally like to do, but we can prototype it very, very quickly. So this is completely off the shelf. We just got these sensors, we plugged them together, we programmed them, and our whole payload is now ready to go. How long do you think it took us from sitting down and going, okay, we need to do something, we're going to rapid prototype the whole thing, to actually having the first one, we actually printed 2 in the end, having the first one in our hands physically, actually working, having passed testing, so all the logger and everything's working. Any ideas? A week. Close. 10 days. So 10 days we sat down and we said, right, okay, we really could do it. Andrash, who's outside, sat around, drew the CAD the CAD designs for us. I built the Gadgeteer internals, and within 10 days we could rapidly prototype. The advantage here is if someone came along and said, oh, I've got this other sensor, one of you want to do your science, I have this other sensor, we could very easily plug it into this within a few days perhaps even. We could plug it into this and actually have that logging as well, and so we're good to fly. Now, we were going to cut to a video, and I'm getting the no thumbs up here, which means that we probably haven't managed to launch it, or we're still competing with this aircraft that's coming in. So I'm going to show you a picture of what it would have looked like. You should always have one of these in your slides. So the good thing about this picture is that you get to see basically how we launched. This is our first generation one, and this is how we launched it. The really good thing about this picture is that you can't actually tell how cold it was that day, because it was freezing, I can assure you. So on the very extreme left, you have the big balloon, and in the next person in, that's Neil, has a parachute. It's a very small and very simple parachute. There's a reason for that. You don't want something that's complicated and deploys, because the more complicated something is, the higher the chance of failure. The next one up is the payload. This payload's actually quite interesting. We'll probably see a picture later on. This payload's quite interesting because we did it in 2 packages, so one package could see the other. And then we have the final check at the end, which is a camera, and the guy at the end there with his thumbs up saying we're good to launch. And so that's what you would see today, except the bit in the middle you'd replace with our sphere that we've got. So that's the first thing that we're really, really excited about, actually. And probably it's worth talking about the first generation. So our first generation of data logger, we were sitting around going, look, data loggers are expensive, we've got a prototype. Why don't we just use a phone? Hey, why don't we just give this a go? And so we flew a phone, and it turned out it was really successful. So successful, we're actually flying one in our second flight today. Incidentally, by the way, we have a Twitter hash, which is Sutton Astra. I've got it at the front and the end of these slides, if you want to see how these flights progress throughout the day. So our second flight that we're hoping to launch is actually has a phone. And the reason that we really like this is because, your phone has accelerometers. For all intents and purposes, all it really is a box of sensors with a processor. And it's gone through all the ruggedized testing. How many times have you dropped your phone and thought, wow, this thing's really strong, yeah? So these are the sort of things that we're looking for. So we have accelerometers in them, we have GPS, there's a massive amount of storage in it. It's also got network connectivity, and this is something that we're sort of experimenting with, because at what altitude does your phone not work? Theoretically, we're hoping to get it into the many thousandths of meters. So far, I think we're up to about 2,500 meters is our last connectivity. The reason this is very important for us is because the phone can send us a little piece of information back that says, hey, I'm here. And we can update our prediction model, because we can say, well, we know we launched it from here, and we expected it to be here, but oh, it's actually here. So just like the weather forecast kind of gets it wrong for the next 7 days, as you get closer to that 7th day, the forecast changes. We steer our prediction code exactly the same. So as we're traveling along, because at some point we have to go and collect this, at some point we have to go and find it, and in order to do that, we can follow our little bit of tracking code. The interesting thing about this is, for us anyway, that we have an Azure worker, so this is actually using cloud compute, because we don't do an awful lot of launches. But when we do a launch, we need quite a lot of processing power, and so we just rent our processing power in much the same way that you sort of have Hotmail and things like that. You're just using a cloud resource. We use the same thing, but for compute power. So very quickly, we just rent a whole pile of machines just for one day, do a lot of computations, run our prediction code, and away we go. This is one picture I must admit I really am quite happy about. This was our first generation launch, and this was using the phone. And we thought it'd be quite good just to take a picture of the phone with the curvature of the Earth behind. So this is at an altitude of 19 or 20 kilometers. And you're actually beginning to see the curvature of the Earth there. You can actually see the atmosphere. You can see it sort of tailing off into a very dark at the top. And so, yeah, that's one of the highest. We probably reckon that's one of the highest Windows phones around. This is to give you an idea of our prediction code. So as I said, over the last 100 years, people have been releasing balloons with sensors of some description on them. And even today, we release lots of them. But it's this retrieval aspect that we're really keen on. This here gives you an idea. So this is Astra 8. So this is the mission just before the one that we're hoped to have launched today. And this just gives you an idea. We can superimpose this on a map, and this gives you an idea of the sort of prediction that we get. So the circle that you see at the very bottom left-hand corner there is where we release it from. And you can see that it gradually goes up. Now, it's not very simple. You can see that there's a crosswind there, so that it goes in a little bit of a zigzag. And at the very top there, the balloon bursts. I can't remember the altitude of this one. I think it's maybe about 14 kilometers. Don't quote me on that. And the balloon bursts. And then you can see that it comes down on the parachute. And if you probably make it out at the back there are some red ellipses, and those are our initial predicted landing site. And where we actually landed was just within the 65%. So we were quite confident with that. Obviously, we're improving the prediction model, but we were quite happy with that. And you can see from this that it's quite a complicated flight path that it takes. So the first launch, Gadgeteer, fully rapidly prototyped. And the second one, we're using a phone and with some sort of cloud compute behind this. There are some other pieces of technology that we're also investigating, which we're flying on today's missions. One of them is a very small satellite transmitter. It's just a standalone satellite transmitter, and we should be able to switch to that in a minute and see where things are. And we're also experimenting with very long-range communications. It turns out communication is always a real pain. The minute you've let go of something, once we let go of it, and I'm like, I can see it, it's there. It never said hello to us. That was it. We never got any data back from it. And communication is a massively, massively big issue for us. So we have this thing called an RTTY module. It's a very small module. It sends back very small amounts of data. It literally just says, hey, I'm here. It's a community type thing. So we broadcast to people that, hey, look, we're looking at doing this launch. Here's our tag. We're broadcasting on this frequency. If you happen to hear of any of these pieces of data that we're broadcasting, please send them to us. We're really interested in them. And we have a series of people that are signed up. People are really excited about the launch today. This long-range transmitter, we're potentially going to get 500 kilometers out of it. There's a secondary one on that which will actually bounce off of the lower atmosphere so we can start going over the curvature of the Earth. And so that's very exciting. So maybe I'm actually just going to see if I can swap to that for you. Hold on, hopefully my windows are still open here. So the first one, let me just change my tag here. So this is our very long-range transmitter. The little transmission towers that you see here are people that have volunteered to help try and track our balloon. So if I just zoom out a little bit here, you should begin to see, let me just zoom out a bit more. As that loads, what you'll see is little control towers, which are people, you know, in their garage or something, and they've said, okay, we're willing to help track this for you. And we're broadcasting. So I can see from here that they're probably still sitting outside in the field here with it. And you can see, so there's a little bit of inaccuracy there. You see that very long straight line? That's where we were getting a GPS fix. And then you can see that they've walked out onto the grass already to have an attempt, which was us earlier this morning. And there was an Apache came in to land, and then there was another aircraft came in at at 11 o'clock. And we have to get our time slots. So we're battling with the wind and time slots. So we'll see if that updates. The other thing is that we're getting a lot of different types of data back. So here's an example of one that when we were testing it earlier on. And you can see that we're beginning to get some sort of lat longs back. So this is the sort of data that we get. We have this all stored elsewhere, but we thought we would just broadcast it onto Twitter to give you an idea of the sort of data that we have. And finally, if you are interested, this is our hashtag here. So keep an eye on it if you wanted to see how some of our missions have ended. And I see I'm almost out of time, so I'm just going to switch back and say, well, where are we going with this? Okay, it's one thing to say, hey, look, I want to get my sensor back because, it's valuable to me, but maybe at some point the sensor's not worth that much and you don't want to be littering. Why doesn't the sensor just fly home? So we have another project at the University of Southampton where we're looking at this very problem. So when the balloon bursts, or before that, at some sort of altitude, you can say, actually, I tell you what, release the glider. So the picture on the extreme left there is actually one of our test gliders tied to a balloon, and we're doing a release test on it there. Now, there are some civil aviation rules that we're having to look at here, and so we have designated danger areas that we do this testing. But the overall concept is that basically you either have an autopilot in the glider, and when it releases, you say, hey, fly home or fly to this waypoint here, and then you drive there and pick it up, which we think is quite a nice solution. We've got a variety of different gliders built, so the top, actually both of those have been built, and you can see the test one that we have there. So I realize that's quite a crazy collection, and I'm sorry we couldn't get switched to the video, but maybe we'll put a video online of the launch if we get to do it today. But what I wanted to sort of show is that, there are 4 people out in the field there, 5 people out in the field there, who are part of the team. We all come from different disciplines. My background's computer science, there's aero guys on it, there's mechanical people on it. We all come from different backgrounds, and we all work together on what we actually think is actually quite a cool project. And, we're developing this capability to fly sensors, but we look at you, the next generation, as a generation that's going to come up with the science behind this and the reasoning about why you want this sensor to be flown through this piece of space. And so, finally, I'd like to say a big thank you, obviously, to Microsoft for inviting us to come here today. But like all good projects, it's not the guy that stands at the front of the stage that does the work. There's a whole collection of people that have done a lot of work here, and thanks really goes out to them. And thank you for your time.